Okay, as we start chapter 3, we're going to start talking about our concept of a derivative. Now, a derivative is a really important function in math, and it really does help us with a slope that we're really familiar with, and that is slope. Now, slope in general, you've all seen slope. Slope is simply, how a line tilts. It's the old rise over run. It's the change in y over change in x. We reviewed this earlier this year. Remember, there's formulas for slope. We could say slope is y2 minus y1 over x2 minus x1. But that's all kind of measuring how a line rises and falls. So if I look at something like this, then I can easily find the slope. I can pick a couple points on this line. Maybe I pick this point, which appears to be 3, -2, and I can pick this point, which appears to be 6, 0. And I can find the slope of that line. -2 minus 0 over 3 minus 6, -2 over -3, so it is 2/3. No problem. So this line is going up 2 as it goes over 3. That is its slope. Now the problem is, how do we find slope of something like this? Now this is some kind of curve, some kind of cubic curve, I believe. So I can't necessarily find the slope of this line, and it's definitely not going to be the same. If I pick 2 points, if I pick these 2 points for say, and I use the general slope formula, then I'll get a negative slope because if I connect it, these would be going down. If I go these 2 points and think about that, well, this case, the slope will be going up. So it kind of makes sense though, because in a curve like this, sometimes it's going up, sometimes it's going down. So we really want to know really how a curve like this is changing. How is its y changing in comparison to its x? Now, unfortunately, on something dynamic like this, it's not as simple as a single formula. This is where we're going to have to introduce the definition of a derivative. Now, before we do that, we'll kind of go through the basis of how a derivative, how it comes about, how it's created, how we can find slopes of these curves, and what we're actually looking for. So to find the slope of a curve, we typically will estimate it, the slope of the curve of any curve. So we'll say the slope of f of x at some point, I don't know, we'll say x1, y1, some point on the curve, is going to be the same as the slope of the tangent line at that point. So here is a really important concept of a tangent line. Now, if you remember from geometry, the concept of tangential lines and segments, use them a lot in circle theory. So here's a circle, center C. So a tangent line is a line that is going to be touching the circle at just one point on the outside. So if you take a pencil and put it on the side of a quarter, they should only theoretically touch at one point. That is a tangent line. So we have to find the slope of that tangent line. So just writing some, estimates. So maybe one here looks something like this. Kind of touches only at one point. Over here it might look something like this. Over here it might look something like this. Okay? So it changes depending on what the point is. And calculating this can be pretty tricky. So the way we're going to calculate it is we're going to talk more about the difference between a secant line and a tangent line. Now we won't use secant lines a lot. I'm going to really use it to prove how a derivative comes about, how we find slope and things like that. But in general, we're definitely more interested in a tangent line than a secant line. So a secant line of a graph is just going to be a line that connects any 2 points on the graph. So you just pick any 2 points and you connect the dots. So if I go back up here, if I want a secant line, maybe I do just connect these two red dots. That would certainly be a secant line. But if we want the slope of the curve at a given point, we can't use a secant line because it definitely touches at two spots. So a tangent line, that's the line we're really more interested in. That's going to be the line that meets the graph in only one spot. And it's really in only one spot in some kind of general neighborhood, because if you go on, it might hit again somewhere. But in a small neighborhood around a value, we want it to only hit in one spot. So how am I going to find the slope of this tangent line? How am I going to find the slopes of these curves at the given points? So the theory is a little intense, but eventually I will promise there'll be some really easy rules that will definitely make this a little easier. So what I'm going to do is I'm going to go through an example where I'm going to find the slope of a tangent line of x squared at the point 1, 1. Now, if I do the graph of x squared, I'm just going to plot some points that are on x squared, something like this. So this is x squared. And I want to find the slope of the tangent line at 1, 1. So 1, 1 is the point right there. So just estimating it, you can kind of think of the tangent line as going up somehow like that. But I want to estimate what its slope is at that point. Okay. So what I'm going to do is I'm first going to make a secant line. I'm going to do a series of secant lines. So first thing I'm going to do is I'm going to pick a point that's kind of close to it, but not very close. We'll say 2, 4. So I have 2, 4, and I have 1, 1. So if I connect these, I get a secant line. And this touches the graph in two spots, so it is a secant line. Now the nice thing is I can find the slope of this secant line. It's 4 minus 1 over 2 minus 1. It's 3 over 1. So my idea is now that is not a tangent line, but I do have the slope of a secant line that's pretty close to the tangent line. So what I'm going to do is I'm going to do a better estimate. What we're going to do now is this distance, this x distance between these 2 points. Currently that x distance is 1. From 1 to 2, that's an x distance of 1. Maybe I cut that distance in half. So if I cut that distance in half, I'll have a point that's closer to 1, 1, but you'll get a different secant line. So I'm going to go over to this graph here. I'm going to do the same exact thing. Here is my x squared again. Now I'm going to continue to use 1, 1. But this time, instead of using 2, 4, I'm going to get an x value that's closer to it. Maybe I'll use 1.5. Now, how could I possibly find the y value at 1.5? Well, we know y is x squared, so y is just 1.5 squared, which is 2.25. So now if I connect these 2 points, they will obviously be a little closer together, but it's still a secant line. So you get this. And now I can find the slope of that line, 2.25 minus 1 over 1.5 minus 1. That's 1.25 divided by 0.5, that's 2.5. So by getting the x values closer together, the slopes of the secant lines got smaller. Now, this process where we're basically taking this distance, the first distance we said between the x's was 1. In this case, we were going from 1 to 1.5, so my distance was 0.5. So how we will eventually find the tangent line is we're just going to make that distance smaller and smaller and smaller and smaller until it approaches 0. So this concept of approaching a number is what we talked about with a limit. So let's do one more. Let's pick a point even closer to 1. Let's make it super, super close this time. And then we'll see if we can't guess what our slope is probably going to be. And then we'll find the official definition and see if we were right. So here's 1, 1 again. I'm going to pick a a point so close that we could probably, 1.01. Like you could barely see the difference because, you know, the difference in this case is just 0.1. So to find the y value, y is x squared. So we'll take 1.01 squared. So when I do that, I get 1.0201 for my y value, 1.0201. So now my secant line is really, really close to the tangent line because the difference in those are, now it's still a secant line because it's going through 2 points, but it's really, really close. But now if I do the slope of this line, 1.021 minus 1 over 1.01 minus 1, I get 0.0201 divided by 2.01, which is 2.01. So my slope went from 3 to 2.5 to 2. And so if you think about it, what would you guess the slope of the tangent line really is? Well, I'm going to guess the slope of the tangent line. I'm going to guess it to be 2 because we're at 2.01 and I can keep making it smaller and smaller and smaller. I can make that distance smaller and smaller and smaller and get the slope closer and closer and closer to 2. So the idea is because we keep getting closer and closer, we can use a limiting process to find these slopes. Now, there is a generic formula to find the slope of a tangent line at point A, and it's given by this. It is the limit, this tangent point at A is the limit of A plus H minus f of A over H as H goes to 0. Now, this might look really complicated, but it's exactly what we just talked about. F of A plus H is the y value at a slightly bigger point than H. So it's at A plus H. So you take the A value and you go a little bigger, like we did the 1 and we did 1.01. And then this is just simply the y value at A. And H is that distance between the x's. So as that distance becomes smaller and smaller and smaller, basically going to 0, we can have this idea of a tangent line. So just because we have space here, let's go ahead and just go ahead and verify. Let's just use this on the previous problem, and then we'll try it with a different one. So the last problem we had was y equals x squared, and I wanted to know the slope of the tangent line at 1, 1. Well, if I use this idea, the slope of the tangent line is going to be the limit as h goes to 0 of f of a plus h. Well, a is 1, because that's our x value. So it's going to be 1 plus h squared minus f of a. So I'm going to plug 1 in for that. So that's just 1 all over h. So this becomes the limit as h goes to 0 of 1 plus h. Well, if I just FOIL it, it's 1 plus 2h plus h squared minus 1 all over h. So this becomes the limit as h goes to 0. You'll see these 1's cancel. And you could also see they all have an h. So this just becomes 2 plus h, because I'm going to divide this and this by h. Well, now if I put that in there, I just get the limit as 2, or as h goes to 0, of 2. So that just gives me 2. So the slope of the tangent line is 2. Now, we did it informally. We got 2.01, and we felt like we could get that even smaller. Well, this is actually showing that that limit actually is 2. Now, there will be a much, much, much easier way to do this. This tangent formula to find slope, it is, in fact, true, but we really use it to find the function that will find these slopes of tangent lines much easier. So let's look at this example. Now, this is somewhat incorrect because this should be at the point 1, 2, but just to put it there. So if I want to find the slope of the tangent line here at basically my a is 1, because that's my x value, I'm going to be finding the limit as h goes to 0 of 1 plus h cubed minus 1, or minus 2, pardon me, because it's f of 1 over h. So now we have to FOIL this all out. So I know from earlier, if I do 2 of them, I get 1 plus 2h plus h squared times 1 plus h minus 2 all over h. And then I also have a plus here, one here. That's because it's x cubed plus 1, pardon me. So we have that. So now I have to multiply all that out. So I get the limit as h goes to 0. So I get 1, I get 2h, I get h squared, and then I'm going to multiply everything by h, so I get plus another h, I get plus 2h squared, and then I get plus h cubed, all minus 2 over h. Well, if you notice, the 2, I have the plus 1, I keep forgetting to write there. These two ones and this 2 divide out, cancel out. So this gives me the limit as h goes to 0 of 3h plus 3h squared plus h cubed all over h. But now you can see they all cancel, so this just leaves me with the limit as h goes to 0 of 3 plus 3h plus h squared. So this goes to 0, this goes to 0. So my slope is just 3. So if I were to graph x cubed plus 1, look at the point 1, 2, the slope of the tangent line should be about 3. Now we use this informal definition and this kind of more formality that we got the slope to come up with the concept of a derivative. Now we've talked about a derivative before. Well, a derivative is just a function that will find the slope of a tangent line at any point x. We call it the derivative. Now the nice thing is the math we did in chapter 2 is how we find the derivative. So it's actually a really easy thing to find. So the notation for the derivative, there's lots of them. Sometimes we call it f prime. The little dash you'll see, we call it prime. Or this is y prime, dy dx. Whenever you see the d notation in calculus, it means change. So essentially dy dx means change in y over change in x. That should sound familiar because it's the same thing as the slope definition we talked about earlier. So if you want to find the derivative, then you can find the slope of the tangent line. Because once I have a derivative, let's say I have the derivative, f prime of x is x plus 2. That's the derivative of some function. Well, if I do f prime of 1 and get 3, what that's going to tell me is the slope of the tangent line at x equal 1 is 3. Now, and then if I wanted a different tangent line, I could put a different number on. The derivative is a very, very generic function that will find the slope of the tangent line at every given value x. And it has lots of other things too, but the big thing is it does that because in that case, you can estimate the rate of change of a curve using its tangent line. So we're going to practice these a little bit. We're going to see how they work. We're going to do lots of different types of examples. And then after we get to this section, I will tell you there are lots and lots of shortcuts to find derivatives, lots of algebraic rules and things we'll learn for the next 3, 4, 5 sections. But for now, we want to use this formal definition of a limit. So I'm going to start with a line because we already know what the slope of this line is because it's already got y by itself. So the slope of this line is -4. That is not very tricky. Its slope at every point is -4 because it's a line. But I'm going to find the slope of the tangent line using the derivative notation. So what I'm going to do is I'm going to find the derivative of this function. I'm going to find f prime of x. Write this down a lot because you're going to be doing this definition this whole section. So limit as h goes to 0, f of x plus h minus f of x over h. So now I'm just going to plug these things in. I'm going to plug x plus h into the function. So everywhere I see x, I'm going to put x plus h. So -4 times x plus h minus 7. So that's the first part, minus the whole other function. So I'm going to put it in parentheses, -4x minus 7 all over h. So now if I do a little bit of algebra, I'll get negative 4x minus 4h minus 7 plus 4x plus 7 all over h. And not surprisingly, the x's go away, the 7's go away. So this just turns into the limit as h goes to 0, negative 4h over h. The h's cancel, and we are left with negative 4. So what this says is the derivative function is negative 4. So if I want the slope of the tangent line at 4, I could plug in 4, but it's a constant function. It's saying the derivative is always negative 4. So the slope of every tangent line is always negative 4, which makes sense because this is a line. If I graph this, it looks something like this. Well, if I say a point 4, which is somewhere down here, well, if I lay a line right on top of it, tangent, well, it's going to be the same line. Tangent lines of a line are just its line itself. So not a very interesting one for a line, but it's a good one to see how the definition works. Plugging this into the function, this is the original function over h, and then just some algebra. But this is that algebra I forewarned you about in the last chapter, that once you get this set up, it's exactly the stuff we've been doing. The math we did in chapter. Let's look at this one. So we're going to find the derivative. So we're going to find, I don't know, we could find h prime of x. So this is going to be the limit as h goes to 0. Now remember, it's f of x plus h. So we're going to put x plus h into that function. So x plus h squared. Don't forget that negative sign out in front. Plus 4. Got to remember that plus 4. I kept forgetting that on the cubic one earlier. Minus negative x squared plus 4 all over h. And then we have to simplify this. So this becomes the limit as h goes to 0 of negative x squared plus 2xh plus h squared. Hopefully you remember the expansion of this, x plus h, x plus h foiled. If not, you can certainly take your time to do that. But there is a minus out in front, so that will be important. Plus 4 plus x squared minus 4, because I'm distributing that negative, all over h. So the limit as h goes to 0 of negative x squared minus 2xh minus h squared plus 4 plus x squared minus 4 all over h. Now, for our derivatives, we're going to do it the long process. If lots of things don't cancel out, we're going to be in trouble. But you can hopefully see that lots of things do cancel out, just like they did before. So h prime is going to be the limit as h goes to 0 of negative 2xh minus h squared all over h. Hey, but nice news. Everything on the top has an h. So this is simply going to be negative 2x minus h, because I'm canceling one h here and one of the h's here. Well, now I can put 0 in for h, no problem. I will get a function. I get negative 2x. So h prime of x, the derivative of h, is negative 2x. Now, since this is a function, it does change. If I wanted to know the slope of the tangent line at x equal 4, I'd plug in 4, and I get negative 8. If I wanted the slope of the tangent line at 0, it would be 0, because I get negative 2 times 0. So the slope of the tangent line changes as the points in the graph change, but if you have your derivative, you're just changing the value of x in that derivative to change the slopes of the tangent lines. Okay, let's look at this one. Now this is a fractional one, but it's the same thing. I've used different notation here, dp dx. If you want to use p prime x, that's fine, it's the same thing. We're finding the derivative of this function. So this is, again, it's going to be the limit as h goes to 0. First, we will plug x plus h in for x, so we get that nasty fraction, minus 1 over x plus 3 all over h. Now, we did one of these earlier as well when we have these two kind of gross fractions. the key to doing a problem like this, and we're going to kind of do the examples. We're doing a fraction, we did a quadratic, we did a linear, we'll do a square root, and that's pretty much the only ones we're going to do with this formal definition because it is so tedious. So the way we did this one is we said we'll get common denominators. So I'm going to multiply x plus h plus 3 to this one on top and bottom because that's what's missing between these two. And this one I'm going to add x plus 3 on top and bottom. So what that's going to give me is x plus 3 minus x plus h plus 3. And again, there is a minus here, so that minus is going to have to be distributed eventually over my common denominator, which are these two expressions over h. So if you get to this point, you're in pretty good shape because now it's just a bunch of canceling. So as h goes to 0, we have x plus 3 minus x minus h minus 3 all over x plus h plus 3 times x plus 3. Now it's all over h, but remember, this is h over 1. So I can also write this as multiplied by the reciprocal, 1 over h. We're going to do it eventually, so I'm just going to write it at this point. X's cancels. 3's cancel. So let's write where we are at this point. So we have the limit as h goes to 0 of negative h over x plus h plus 3 times x plus 3 times h. Well, but hey, look, those h's cancel out. So now we end up with the limit as h goes to 0 of negative 1 over x plus h plus 3 over x plus 3. Now, this is not 0 over 0 as a limit, so I can plug in 0 here. And so what I end up with is negative 1 over x plus 3 squared. That is p prime of x, or dp dx. And that's true because if this is 0, then they're the same thing twice. So this fractional function has a derivative that is a fractional function as well. Okay, so the last thing we're going to do is now that we can find the slopes of the tangent line, because we can find the derivative and plug an x value in to find the slope, now we'll actually find equations of tangent lines. But once you have the slope and you have a point, really it's no different than what we did earlier this year where we're using y equals mx plus b and finding the equation of a line, because we'll have a slope, we'll have a point, and we'll find the line. So of course, the first thing we're going to have to do is when we find the equation of a tangent line through these following functions, we're going to have to find the derivative. But the nice thing is, and the reason you can always tell if you're doing this correctly, if I graph this function in Desmos and then I graph the tangent line I get, and I definitely encourage you to do that, then you'll see that the line will touch the graph at one point. So let's first go ahead and find the derivative of this function. We have a squaring function. Now, this one's kind of a little less fun because first we're going to plug x plus h in for x. Well, now in this case, there are two things with x. So it's x plus h squared minus 4 times x plus h. Then we're going to subtract the function. So we're going to subtract x squared minus 4x all over h. So now, same thing, we'll expand x plus h squared. So that's going to be x squared plus 2xh plus h squared minus 4x minus 4h. And then over here we'll get minus x squared plus 4x all over h. So good news is a lot of this will cancel. Always does. X squared and x squared, 4x and 4x. I think that's it. So f prime of x is going to be the limit as h goes to 0 of 2xh plus h squared minus 4h all over h. Hopefully you're starting to see a pattern though, because the pattern says, well, they're all going to have an h, so the h's are going to cancel out with a lot of them. So this is going to end up being the limit as h goes to 0 of 2x plus h minus 4. Well, now if we plug in 0 for h, we are just left with 2x minus 4. So f prime of x is 2x minus 4. So this is our derivative. This is our function that will do the slope of the tangent line. Now I want the tangent line at 1, 3. So my x is 1 and my y is negative 3. So my slope of my tangent line is simply going to be f prime of 1. I'm going to plug 1 in for x, because whatever number I plug in, that's the slope of the tangent line at that point. So that is going to be 2 minus 4, which is negative 2. So now we are essentially back to algebra 1. We want to find the equation of a line with a slope of negative 2 and a point of 1, negative 3. So this is what we did earlier. We used y equals mx plus b. So we get negative 3 equals negative 2 times 1 plus b. So b is negative 1. So our tangent line equation is y equals negative 2x minus 1. So I would encourage you, pause this video, go to Desmos, graph this function, and then graph this line. Look at it and tell me, does it appear that that line is tangent to the curve at that point? All right, let's look at one more. So this one is a square root, and so this is going to get back to those fun problems we had where we had those crazy square roots. Now, one mistake I did catch on here, this is going to be 1 square root of 2, because if you plug in 1, you get 1 plus 1 is 2, but it's the square root of 2. That won't come in until later, but I did notice that. So I'm going to find the derivative, so I'll find y prime, or dy dx, whatever you want to call it. So y prime is going to be the limit as h goes to 0 of square root x plus h plus 1 minus square root of x plus 1 all over h. So this should look really, really familiar because we all love these kind of problems. So we're going to multiply by x plus h plus 1 plus radical x plus 1 all over radical x plus h plus 1 plus radical x plus 1. So when we did these before, and it doesn't change, it's the same math now. Now that you got it plugged in, it's the same stuff. We FOIL these, we get x plus h plus 1. We know the inner and outer cancel. So this is minus x plus 1. Same thing, got to make sure that we put that in parentheses. H on the bottom, square root x plus h plus 1 plus radical x plus 1. So now the stuff on the top is going to become x plus h plus 1. No, I don't want to drop my limit notation. So it's x plus h plus 1 minus x minus 1. Very important to have those parentheses. Over h, x plus h plus 1 plus radical x plus 1. Cancel, 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 cancel. So we just have h. But the h's cancel as well. So we just have the limit as h goes to 0 of 1 over square root x plus h plus 1 plus square root x plus 1. Well, now if I put 0 in for h, that's fine. I'll have x2 of the same thing on the bottom, so I'll get 1 over 2 radical x plus 1. Because I have an x plus 1 here, and when you put 0 in, I get another x plus 1 here. So that is y prime. So now I have to find the slope of the tangent line, but that's going to be pretty simple because I'm finding the slope of the tangent line at 1. So the slope of the tangent line, I'm just going to put 1 in here. So that's 1 over 2 times 1 plus 1, which is 2. Well, that's a really gross slope, 1 over 2 radical 2, but it is what it is. And now I'll find the y-intercept. So y equals mx plus b. So y is radical 2. M is 1 over 2 radical 2. X is 1 plus b. So here's how gross these can turn out to be. You can get some pretty nasty ones because this is going to be radical 2 minus 1 over 2 radical 2. That is your y-intercept. And our equation of our tangent line is going to be y equals 1 over 2 radical 2 x plus radical 2 minus 1 over 2 radical 2. So the last one turned out much nicer, but when you get square roots, it definitely can do this. So again, graph this one, graph this nightmare, and in theory, it should be tangent at that one point on your graph. So this is the first section. This is the very formal way of derivatives. Like I said, there will be shortcuts coming, but really important to know where this thing comes from, what the basis of it is, before we start just calculating them.